subject to some conditions, functions are guaranteed to have maximum and minimum values. Here is the extreme value theorem. It says that if a function f is continuous on the closed interval ab, then the function attains a maximum value and the function attains a minimum value. If you don't like this, you can make it a little bit more precise. Here's a slightly more precise statement of the extreme value theorem. It says if a function f is continuous in the closed interval ab, then this is really just making clear what I mean by attains a maximum value and attains a minimum value. Right? What I really mean is that there's some point c and d in this interval, so that no matter what other value I pick in that interval, f of c is less than or equal to that other value, and f of d is bigger than that other value. So f of c is the minimum value. C is where f achieves that minimum value, and f of d is that maximum value. D is where the function achieves that maximum value. The extreme value theorem promises us that these extreme values exist, but it doesn't tell us how to find those extreme values. I mean, you could have a complicated looking but continuous function on the closed interval between a and b, and it might be hard to actually determine where the maximum value occurs. But the extreme value theorem tells you that the maximum value is achieved somewhere on that closed interval. Nevertheless, even in that example, there are extreme values. It's just hard to find them. Now, maybe that all seems obvious. Well, one way to understand the extreme value theorem is to try to break it. Try to mess with it somehow and see if it still works. This is sort of the car method to doing science, right? If I'm studying cars and I want to know what's important to making a car go, well, I should just take off the wheels and then see if the car still works. Doesn't work so well, right? The fact that the car doesn't work when I break the car's wheels off tells me that the wheels are important for the car, right? Same game with this theorem. I want to figure out what the important parts of this theorem are, so I'm going to try to break this theorem in various ways, and if the theorem doesn't work after I break it, well, that must have been an important part of the theorem. What if, for instance, we were studying a function on the domain 0 to infinity, including 0. So yeah, what if instead of closed interval between these two numbers, a and b, I'll have infinity be one of those numbers. And of course then I have to make that an open parenthesis there. So if a function is just continuous on the interval between 0 and infinity, including 0, does that mean that it actually achieves its maximum minimum values? Well, no. Think about this example. The function f of x equals x defined on that interval. This function does not achieve a maximum value. If you tell me that some number is the maximum output of this function, I'm just going to add 1 to whatever you say, and that'll be a bigger output to this function. This function does not achieve its maximum output at any given input. What if we were studying a function on a domain that was an open interval? Yeah, so what if instead of closed interval, I just said open interval between these two numbers, a and b? Well, then the function would not be guaranteed to have a maximum or minimum value. I mean, take a look at this. Here's an example of a continuous function defined on an open interval between minus pi over 2 and pi over 2, and this function does not achieve a maximum or minimum value on this interval. I can make tangent as positive or as negative as I'd like by choosing x close enough to one of these endpoints. What if I tried to mess up the extreme value theorem by eliminating the condition that the function be continuous? So yeah, what if I break the statement of the extreme value theorem by removing the continuity condition? So I'm not requiring the function be continuous anymore. So if it's just some function that's defined on the closed interval between a and b, does that guarantee the function achieves its maximum minimum values? No. Here's an example. Here's a picture of a graph of a discontinuous function, and it's defined in the closed interval between a and b. But here you can see that it's approaching some value but never achieving that value. And here it's approaching some value but never achieving that value. So this function does not actually attain its maximum or minimum value on this interval. To get a better sense of what's going on, here's a much fancier way to talk about the possible output values of a function. So let's write I to represent some interval. It could be the open interval between a and b, the closed interval between a and b, whatever, right? I is just a set of numbers. What's f of a collection of numbers? What does that even mean? Well, this is the collection of all the output values if the input is in I. So f of I is the set or collection of all the f of x's whenever x is some point in the set I. And people sometimes call this the image of I. We can use this terminology to rephrase what we've been talking about. For example, the continuous image of a bounded interval like this interval between two numbers, need not be bounded. So here's an explicit example that we've already seen. Take a look at this continuous function, tangent of x. So I'm going to look at the continuous function, and I'm going to look at the image of some interval. Here is an interval. And what's the output of this function if the input is between minus pi over 2 and pi over 2? Well, the output can be anything, right? So f of I is all real numbers. So even though I'm starting with things that aren't very big, the output is as big or as small as I'd like it to be. What if that bounded interval is also closed? A much fancier way of stating the extreme value theorem is to state this result, that the continuous image of a closed bounded interval is a closed bounded interval. You can really try this for yourself. So you write down some crazy continuous function, so who knows what this continuous function might be, some continuous function on some interval, which I'll call I, between two numbers a and b. So it's bounded because a and b are numbers, right? And it's closed because I'm using the square brackets. And then I want to think, well, what is all the outputs whenever the input is in I? Well, this is just going to be the closed interval, right? What's the smallest value? Well, that's the minimum value that the function achieves. And the biggest output is just going to be whatever the maximum value is that this function achieves. So this statement, that a continuous image of a closed bounded interval is a closed bounded interval, is really getting at the same idea as the extreme value theorem, saying if you start with a continuous function on some closed bounded interval, then the outputs are just going to be between, including the minimum and maximum value. And the fact that these are square brackets here, the fact that this is a closed interval, is crucial, because I'm telling you that the minimum value was actually achieved and the maximum value was actually achieved. This way of talking is also useful for something like the intermediate value theorem. So yeah, you could say it's true that the continuous image of an interval is an interval. So if you take an interval and you pick your favorite continuous function, f of that interval is just some other interval. That's the same as saying that all the values in between are achieved, and that's really what the intermediate value theorem is getting at. This is just a very succinct way of stating the intermediate value theorem. The upshot here is that we're seeing there's something really special about continuity. So here again is the extreme value theorem, and what we've learned is that the continuity is really important. If someone just shows you some function and it's not continuous, don't expect that you're going to be able to find any extreme values. They might not exist. It's also really important that this is about a closed interval between two numbers, right? A closed and bounded interval, and that's really important. And if you're being asked to find maximum minimum values not on a closed interval, say, you shouldn't expect that they necessarily exist. They might not be there. So this theorem can help guide you towards the correct answer because it tells you what sort of answer to expect.